Good morning, and thank you so much for inviting us to deliver the SLE Plenary. It's really a great honor, and as Anna mentioned, it's really we were really pleased to have been invited as a duo. In 10 years of close collaboration, it's the first time that an organization really recognizes the value of collaboration for the discipline. So this is very encouraging to see. So today we will be talking about what's on everybody's minds. We already had a panel about it yesterday, AI and the threat to linguistics. Whoops, I'm not used to Windows machines. Yeah. Before I get started, I wanted to give you some pointers in case you're interested in what we do and want to find out more. This QR code leads to the website of our research team, which is called Out of Our Minds, pun fully intended. If you would like to try a few of the things we will be presenting today, you might be interested in the page that gives access to our cloud computing interface, where you can run computational simulations and download embeddings without necessarily having to do all the programming and having access to the infrastructure that this type of research requires. And I also wanted to flag our participation in the MEDAL project, which is an EU-funded project that is led out of Tartu. We have a whole Tartu delegation in the audience. And it's a project that's aimed at providing, supporting methodological excellence in data-driven approaches to linguistics. The project is approaching its end, but all of the materials that we have created are available free of charge online. That includes the materials for our 3 summer schools in corpus linguistics, experimental linguistics, and computational modeling. So I'm going to start with provocation. If you're a linguist and you have applied for funding recently and you have dared to mention that you would like to do something involving computational methods, you are very likely to have been told that, guys, you've had your chance. You've had hundreds of years. As long as we followed your advice, we weren't getting anywhere. And there is this famous quip by Jelinek, who allegedly said in a conference talk in 1988 that every time I fire a linguist, the performance of my speech recognizer goes up. And he's talking about, I've put a picture on there of the IBM shoebox system, which was a system as big as a shoebox that could recognize 16 English words using handcrafted filters, etc., based on the linguistic theories of that time. So this really captures a very long-standing tension between top-down linguistic insights and bottom-up statistical power. And in the age of deep learning, this really resonates even more strongly today. It's somehow still kind of a bitter lesson for the field. We'll get back to that later. So, in a very simplified manner, we could say that there are 2 ways or 2 approaches to knowing language. One is the one that we as linguists subscribe to, and then there is the one that's, dominant in machine learning. And they differ along a number of dimensions. For example, representations. In linguistics, we work with symbolic representations, with abstract concepts that machine learning has completely done away with. Everything's distributed and sub-symbolic. Any learning that we assume is guided by theory. We assume, when you look at L1 acquisition literature, that children will gradually start to approximate the abstract concepts that we assume exist, such as case systems or tense aspect systems. And these symbolic abstract concepts, they are provided by our theories. In machine learning, there is no such thing as case or aspect. Everything is guided by the data. When we evaluate our models in linguistics, we want explanatory adequacy. In machine learning, they want predictive accuracy. And to some extent, quantitative approaches in linguistics have taken on some of the predictive focus, but still, linguists don't like it when you have a paper or a presentation that's only statistics. We want to know what things mean. In linguistics, transparency is, generally high. We know what our concepts represent, more or less, with some discussion left and right. In machine learning, it's at the moment very, very low. And if we generalize, then our generalizations are again theoretically principled, whereas in machine learning, everything's emergent from the data. So modern computational systems leave, I would say a lot, but it's actually virtually everything behind that we as linguists hold dear. There are no parts of speech, there are no syntactic trees, there are no agreement features, there's no case, there's no argument structure, there's not even a direct link to usage instances. Everything is re-represented as numerical vectors. And what modern computational systems run on are things that are completely alien to us linguists. They start with tokenization, and they split text into discrete units that aren't even words. They're something below the word level. Then each of these tokens is converted into dense vectors from an embeddings table. We add, in computational methods, they add some kind of a token, piece of information, to preserve the order of the tokens in the chain. And then in the most recent transformer models, there are multiple layers that are composed of concepts that, we can hardly begin to imagine what they mean. Multi-head self-attention, feed-forward sublayers, residual connections, normalization. I mean, it's not something any linguist has ever encountered in their training. And then the final output is, contextualized token vectors that are used for text, for tasks like next token prediction, which is not a task that a linguist would consider to be, core to our enterprise. So somehow, all of this success has been achieved without symbols, without anything that is core to linguistics. And these LLMs, as you've all had a chat with ChatGPT, they can generate text in multiple languages, they can translate, they can summarize, they can reformulate, they can answer questions, they can pass the Turing test, they can pass professional exams, and the input really is only raw text at scale. And the architecture is, I wrote mathematically elegant, but it's more of a collocation. When I look at it, I think it's actually a total Frankenstein, but it works. It's completely alien to linguistics. And there is a really interesting blog post by Sutton, who concludes that, looking back over the last few decades of computational approaches, that general methods that leverage computation are ultimately superior. So there seems to be some kind of consensus that hand-engineered features have reached, we've reached a dead end with those. Scaling wins, more data, more parameters, more compute, and linguistic intuition is considered some kind of a bottleneck. And the conclusion that is often drawn from this is that what we should learn from this is that there is no point to encode in a system what we think we know. What we must do is design the system so that it can search and learn. Very different from what we as linguists do. We thrive on abstraction, on generalization. We like cross-linguistic insights. We have models of structure, of meaning, of variation. And our tools are there to explain, not just predict. And across the many different subdisciplines of linguistics, there is a very strong focus on either cognitive plausibility, language as a social artifact, etc. Our abstractions are tools, not truths, but some of them are still powerful. What we want to present today is a case study on Polish aspect in Slavonic languages. This is one of those eternal puzzles. Yes, it is. And we wanted to see how well traditional linguistic concepts do in explaining a spectral usage, how more corpus-inspired approaches to language description do in predicting Polish aspect. And then we will compare that with how state-of-the-art large language models do on the same task. So I'm going to present a case study that was conducted in collaboration with one of our former PhD students, Dr. Maciek Borowski. And I'm going to start with the briefest presentation of Polish aspect you will ever have encountered in your lives, just because I don't have time to go into more detail. If you're interested in all the linguistic detail, please scan the QR code. The paper is open access. So aspect in Polish is largely a binary system. We have imperfectives, we have perfectives. There is a very small number of biaspectuals, so verbs that only exist in one form, and that form can be used as imperfective or perfective. There is, even at the formal level, there is discussion as to whether this is an inflectional or a derivational system. I think the field leans towards considering it a derivational system, partly because a lot of the aspectual, imperfective, perfective changes are achieved through prefixation. Now, the literature on aspect in general is exceptionally rich. A lot of it was done during the 20th century and has a very strong imprint of structuralist thinking. There are multiple theories, models, and accounts, but not one of them is really conclusive. So we started out by extracting a set of 1,800 discourse chunks, with which we mean we had our target sentence and 6 preceding sentences so that we could judge the use of aspect in a slightly wider discourse context. And we extracted that from Araneum Polonicum. I put a picture up here of Vlado Benko, who really kindly shared his resources with us. I know there are lots of corpora available for a number of languages, including Polish. They've all been constructed to the highest standards of representativity. But when you want to do computational modeling, you need access to the raw data, which very often you cannot get from a national corpus. So we were very grateful to Vlado Benko for creating a family of corpora called the Araneum family, which includes corpus for Polish. And we sampled 100 discourse chunks for each of 9 aspectual verb pairs. Now you might wonder, why did we take 9 aspectual verb pairs? Well, we chose these 9 pairs to represent a decline of what we call aspectual bias. So to what extent a verb or a pair of verbs is inclined to occur in the imperfective, in the perfective, or occurs in both of them. And I'll show you a few graphs in a minute. This sounds very easy. We chose pairs to represent the decline of aspectual bias, but it's only easy if you have the data to calculate aspectual bias on. And we established this decline based on the behavior of 1,800 verb pairs by using the database created by Björn Wimmer and Marek Łasiński. Really feels like, you know, standing on the shoulders of giants. Other people had done a lot of the work that needs doing before you can even start with this kind of work. And we tracked the behavior of these 1,800 pairs across 10 million sentences. And what we found was the following. So on the left-hand side of the graph, you see the verbs. These are types that preferably occur in the imperfective. So 600 out of our 1,800 types occurred in more than 90% of the cases in the imperfective. On the right-hand side, you see those types that preferably occur in the perfective, and the rest, you know, in the middle goes from virtually only imperfective to virtually only perfective. And what struck me as a linguist is that virtually all of the literature and all of the research has been done on this little bit in the green box in the middle. And those are the verbs that are equally likely to occur in imperfective and in perfective. So when we're looking at the system, essentially, we're accessing the system through part of the system that's not really representative. And I hope Petar doesn't mind me quoting him here, that linguists are a little bit like clinical psychologists. They just focus on that part of the population that's not like the rest. We will come back to that later as well. When you look at token distribution, you see something similar again, with the vast majority of verbs being used mainly in the imperfective. So here's then our table of 9 verb pairs, and you see in the rightmost column the perfective bias. So we go from 0.38 or 38% of cases used in the perfective to 99% of cases used in the perfective. We couldn't go any lower for a number of reasons, but this is the sample that we're using. And I have to go a little bit back in time here. Of course, our question was, we want to do linguistics, but we also want to do linguistics in a way that we can talk linguistics to machines, and we can later on directly compare our results with something we would get from using deep learning. And for this, we relied on a technique that I developed as part of my dissertation, behavioral profiling, which was later published jointly with Stefan Gries and promoted jointly with him, because he developed something similar for a topic he was working on. And for those of you who aren't familiar with this, behavioral profiles, they essentially go back to the distributional hypothesis, where meaning is considered a function of distribution. The meaning of a word derives probabilistically from the linguistic context in which it occurs. So if words occur in very similar contexts, they tend to be more similar in meaning than words that occur in very different contexts. I'm going to be a little bit of a behavioral profile police here, because I get lots of requests to review papers that use behavioral profiling, and it seems like I always find something wrong with them. There are very few things you can do wrong in behavioral profiling, but there are a few fundamental principles that really are important. And one of the things is that I developed this technique as a usage-based corpus linguist. So it's designed to capture usage. It's designed to give you a very detailed snapshot of how the words that you're interested in behave in contexts. So typically, the research question should be couched in usage-based theories, and you need to accept a bottom-up, data-driven approach. A crucial prerequisite is that the labels are naive, and with that, I mean the focus is on properties that could be provided by untrained language users. For example, if you study modality, you cannot say that concepts such as deontic or dynamic or epistemic modality are things that linguistically untrained language users could easily apply to instances in context. So this is, in a way, in this sense, the type of information that you include in a behavioral profile is kind of limited in that sense. Of course, you know, maybe they don't know that there is a past tense, a present tense, or a future tense, but you can ask them whether the action's already happened or is still ongoing or will happen. And maybe they don't know the labels declarative and interrogative, but they know whether they're being asked a question or whether someone's giving them an order. So that kind of properties is what the behavioral profile really runs on. And it's also crucial that when you look at your target sentence, that the annotation is exhaustive. So you don't just focus on the verb you're interested in. You do not predetermine which kinds of elements in the sentence would be important. Say you're working on transitive verbs. A typical thing for linguists to do would be to say, okay, I'm going to look at the subject and the object. But in a behavioral profile approach, you would annotate all of the elements in the sentence exhaustively, not just limiting yourself to a few hand-picked features that you know may be important because they have been used in the literature before. Of course, these features, these hand-picked, predetermined features can be added later. Practically, it's just another column in the spreadsheet, but they're not part of the behavioral profile, and it's important to bear that in mind for the second part where Petar will be distinguishing these two. So typically, when people create behavioral profiles, you will have properties from morphology, from syntax, from semantics, but that's just what we linguists tend to be interested in. You can easily expand the behavioral profile to contain information about discourse, pragmatics, writer, gender, regiolect, text type, font size, whatever you like. And in a sense, the current very powerful machine learning embeddings are a continuous variant of BPs that are categorical in nature. So BPs are discrete. We code the absence versus the presence of a property. And they're also sparse because they rely on manual annotation, which limits the number of features that can be included. Embeddings, on the other hand, are real-valued and dense. They're typically several orders of magnitude larger than standard BPs. If standard BPs have something along the lines of 100 different variables, embeddings can have 300, 700, 1,000 and more. And embeddings also do something really interesting, and that is that they package world knowledge which is not necessarily encoded by behavioral profiles. So just to give you an example, this is from the Araneum Apollonicum. So we extracted the target sentence, which is at the bottom of the slide, with the 6 preceding sentences, because it can be really difficult to assign values to your variables if you don't know the context in which your sentence is being used. So just the English translation, and the system crashed spectacularly, unable to receive and process the data. It's from a newspaper article about the elections in Warsaw. So what would we do then in a behavioral profile approach? We start first by annotating the behavioral profile properties, morphology, syntax, semantics. So it's the verb is a third person, singular, masculine, reflexive, past tense, perfective, expresses figurative motion, etc. And as I said, we can add the theoretical concepts to this, although they're not part of the behavioral profile. So if we're specifically interested in theoretical concepts that have been used to explain a spectral choice, we would add things like whether it's bounded, whether it's specific, whether it's foregrounded, etc. And we don't only do this for our word of interest, we do this for all of the other words in the sentence as well. Now, in one of the talks the other day, somebody says that annotating corpus data is one of the most terrible things you can do to yourself, and I completely and fully agree. After his dissertation, our PhD student disappeared. He went to the dark side and joined industry, where he now works in artificial intelligence, anything, you know, to avoid the manual coding. So we had these 1,800 examples with the 6-sentence preceding context. They were annotated for a total of 54 properties that each had several levels. Even if each property would only have one level, there would be 100,000 data points. Right, so this is an enormous database, very rich in detail. Then from this whole database or network of annotations, you can select the data that you need to answer your question. So maybe you want to know whether you have contextual support for the lemma crash, or for verbs that express figurative motion, for reflective verbs, for the perfective aspect. It's just a way of extracting the data really that answers your question. So just to look in detail at a few examples, we have, you know, example 1 and 2 here, and they have a value yes or no for a number of properties. Then if you say, I'm interested in what the contextual properties are of sentences in which perfective verbs are used, you can extract that. I've expressed it here as percentages. So in 94% of cases, these verbs will be bounded. In 56% of cases, they'll be specific. In 46% of cases, they'll be foregrounded. You know, you can create the profile for either the word or the abstract concept that is of interest to you. So here I've done one for specific verbs. You can see how Vivručić is usually expressed in a large sample of text. Again, I've taken the same properties here, but I could have taken any of the 56 that we had annotated for. And then, finally, I'm getting to the models that we set out to run, and is, in a sense, the preparation that I've done to get you to this point is proportional to the effort that goes into this kind of work, because most of the time you spend preparing, you spend extracting your data, annotating your data. The models you can run, you know, in half a day or less. So we were going to contrast 3 different models for aspect. One model is where we use the behavioral profile and we use the values of the contextual variables to predict the exact lemma. So we had 9 pairs, which means 18 different verbs. A second model is a behavioral profile model, so values of contextual variables, where we want to predict the abstract labels aspect, so whether it's perfective or imperfective. And a third model that we wanted to test is our theoretical model. So we use the values only of the abstract variables to predict the aspect perfective or imperfective. And here are the results. This is a Bayesian model. And I see Natalia in the audience, so I have to make sure I don't say significant. And you can see that overall accuracy of the three models is, reasonably good. If you use the behavioral profile to predict the lemma, you're at about 80% accuracy. If you use a behavioral profile to predict the abstract categories of aspect, you're at 85% accuracy. And if you use the theoretical concepts to predict aspect, you are at 87% accuracy. Now, the difference between the behavioral profile and the theoretical model is not substantial, let's put it that way. But the difference between the theoretical model and that predicts aspect and the behavioral profile model that predicts lemmata is substantial. And there's another interesting difference here, and that is the extent to which these three models predict perfective and imperfective accurately. So you see there is generally a difference between how well they predict perfective versus imperfective, with the behavioral profile models predicting perfective slightly better than imperfective, but the difference is not substantial. The only substantial difference is found in the theoretical model, which predicts the imperfective at nearly 98% of cases correctly, but only achieves 76% accuracy for the perfective. Which is slightly odd, because since many of these concepts come from structuralist traditions, where actually the perfective was considered to be the marked member, it seems to be that the accounts that have been proposed predict the imperfective, the unmarked member, better. We tested our models against behavioral data, so we wanted to see whether native speakers of Polish could retrieve the form that was originally used in the text accurately. It's a little bit like the type of thing that LLMs are trained on, gap filling, next word prediction. And we took 10 verbs, 5 aspectual pairs against, from the data set we had, sampled across the bias spectrum. We had in total 60 chunks, 6 chunks per verb. Participants, 77 completed the entire survey. 57 of these were female, which is very often the case. And we found that the behavioral profile model that predicts aspect only predicts the perfective choices that the participants make. The theoretical model that predicts aspect only predicts the imperfective choices that participants make. But the behavioral profile model that predicts lemmata predicts both aspects equally well. So you can see that there's a real difference between the models that do best when we predict from text to text and the models that do best when we predict from text to actually online behavior of speakers. I'm going to hand over to Petar now, who's going to talk about the comparison to large language models.
Thanks again, and thank you everyone for inviting us again. We really appreciate this. So we wanted to, in follow-up, and I'm also grateful for the opportunity. This is still work in progress, so the second part is not published yet. It's, as I said, work in progress. And the next research question that we thought it would be meaningful to ask is, can linguistic, if we agree that linguists also use specific type of distributed representations, as we saw in these large tables, can they compete with state-of-the-art LLM embeddings? And more specifically, there are ways to change this, because linguistic embeddings or representations are of different kind, and I will go a little bit more about how and why we believe that's the case. They're discrete. They're features that are meaningful, and with LLM embeddings, you have just a long sequence of numbers. So they're dense and numeric. These are, the linguistic embeddings are typically not. But there are ways to turn those linguistic embeddings into meaningful numbers with more or less information translate it into real numbers. And then the question is, can then we compare linguistic embeddings with LLM embeddings and even defeat them? Why not? But I would like you to indulge me for a moment because my background is in psychology, cognitive psychology more specifically, experimental and computational. I fell in love with cognitive psychology, I think, in my second undergrad year, but I was immediately annoyed by representations. That's very central in psychology, especially cognitive, and I think it's also very important in linguistics because it's utterly vague. You can chuck in everything and nothing. And I think in their early criticism, I like this paper from Palmer, appeared in the collection edited by Eleanor Roche. She wanted to cover state-of-the-art of both exemplar models and her own prototype. And there is a very interesting recent study done actually by philosophers of science who surveyed a huge number of active researchers across disciplines, again, neuroscience, cognitive psychology, experimental psychology, and such, so more than 700 of those. They asked a couple of simple questions like, what's your definition of representation? How would you use representation in this situation X? How would you use representation to explain these particular results? And they got probably as many answers at more than 700 different views on what representation is. So it's a mess. And until recently, there was some kind of general agreement among psychologists that we know what they should contain, but we really don't understand how they happen in the mind or in the brain. There's still ongoing research on that, and that's very active domain of research, but they're very, very messy. And with LLM, we changed the name. Now they're not representations. It's hidden in those acronyms here and there, but now you have embeddings. So they're kind of different. We changed the label. We don't know how they're computed because those deep learning networks are too complex to understand, and we don't know what those numbers mean. So they're now completely opaque to us. I think that's interesting as kind of psychological or cognitive psychological phenomenon. So embeddings are obtained over huge, I would say, cognitively unrealistic amount of data because that's not human experience. We don't experience gazillion of words of materials. And they're heavily distributed. They're long numeric vectors. Apparently, according to people who are actively working on them, the claim is they do excellent job across a range of many of which cognitively realistic tasks, and we don't know exactly why, but we're happy that they do. As an opposition, if you think about linguistic embeddings top-down versus bottom-up, linguistic annotations are also rarely, as I said, single point. They're also distributed. You will never have your exemplar say it's past tense, and that's it. You would use more features to describe the sentence, right? They're discrete, they're not real numbers, so they have a bunch of very interesting, unique properties. They're expert-based, theory-driven, and then you could say they're expensive in cognitive sense because you need to invest a lot of time and expertise to make them. They're typically smaller scale. So there is one of these exemplars that Dagmar already used. So you could say some features in exemplar 1 that could be a single sentence or a chunk of sentences. There's some features that are present, others are absent. You can turn that into digits, which is still understandable and easy. However, if you want to start translating those features into some numbers, with assumptions that maybe computers just like numbers more than this discrete representation. So if we transfer those, if we use principled way to translate linguistic features into meaningful numbers, can we do comparatively good job as opposed to large language models? So you can assign some random numbers which are basically numeric IDs for your original features. This -7 doesn't mean anything specific, but it will identify that it's about boundedness. There is a feature behind that number. So it's like your personal tax number or something unique. So this is for a particular feature, you will have the unique number assigned, and it can differentiate whether the feature is the same or different. Then you can just repeat that, but that's very boring and it will not help computer. However, you can add some noise. And that noise can go, you can set the limits. You can say, okay, that -7 can allow anything between -6.5 to -7.5, and that can be unique, or you can have uniform noise. Any number is equally probable, or you can have Gaussian noise. So most numbers are close to -7. Some are further apart between -6.5 and -7.5. So that's still noisy embeddings, but you keep a little bit of information for original linguistics, so you know the feature that is behind that sequence of numbers. But you can do more. If you compare each feature, if you set up your table and look them across exemplars, what you can easily or relatively straightforwardly calculate is how they vary, so each feature independently, and also how each pair of feature co-vary. So are they similar when one is present, the other is always present? That means that you will have high positive covariance. Otherwise, in other extreme, one would be always present, the other would be always absent. It would be high negative covariance, so you can have that for quite easily. Then you can have rate or frequency. This is what Dagmar already presented. She used the percentages, but that's just kind of relative frequency. And then you can also calculate their projections or centers. And from those centers, you can also see how distant numerically they are. So you can start playing with some kind of linguistic space turned into numbers. And you can even do more if you want to superimpose some probabilistic models. So one of the most famous for language frequency, generally speaking, is Poisson. So for Poisson, you need variance, covariance, and rate or frequency. And you can also, if you're a cognitive psychologist, you like your normal distributions like bell-shaped, you can say, okay, it's Gaussian noise. So then you need variance, covariance, and those projections or distances, if you wish. So the approach is the following. You can start, or what we did, we started from original linguistic embeddings, distributed representations, so those theoretic and behavioral profiles that Dagmar just presented. And we also wanted to check whether if we remove certain behavioral profile features which are really low in frequency, whether that will improve the performance. Then, each of these can have 4 more translations into numbers. So 2 of those are random, 2 of those are empirical ones, and then you can compare them with large language models. We also wanted to be comprehensive, so for Polish, we used Herbert, which is most often used, and Roberta, which is apparently most powerful one. How you compare? Now you have the same exemplar, and you have many ways of representing that same exemplar. So you have 2 basic linguistic original ones, then 4 more from those, and then 2 large language models. We set up the ratio of out of 1,800 exemplars, we took 85% for training and 15 for tests. So we have same exemplar, different way of representing them, including large language models. How we wanted to compare them is, I think we made a really good choice because this is the technique called memory-based learning, which means it will not change the representation. It will just faithfully store whatever you give it with the label, with the outcome. So that pair is stored, nothing is altered, it's in original format. And then we use the simplest version of memory-based learning, which is called k-nearest neighbors, which means if you need to assign a label for a new example never seen, so for the testing phase, how many most similar representations you will consider. So small number or large number. And we varied the number of this kind of comparison test from 3, which is the smallest meaningful neighborhood, up to 40, which is, again, cognitively unrealistic, especially if you believe in an old paper by Miller, 7 magical number plus minus 2. So that's much more than cognitive systems should be able to do. Anyways, this is the first result. So you have on the left panel results for imperfective. On the right panel, you have perfective. On On vertical axis, y-axis, you have accuracy from 50% to 100%. 50 is basically guessing. And then on horizontal axis, you have number of neighbors from 3 to 40. Green line are those original theoretic representations, linguistic ones, untouched. And then you have two behavioral profiles. Blue is full behavioral profiles, and red ones are reduced. And from this slide, I will not present reduced behavioral profiles because they do very similar job. They're literally the same. So if you exclude some low frequency features, that will not affect behavioral profiles. So what we can conclude from this first result? So how linguistic embeddings, how well they do. So first, theoretical representations, they do excellent job on imperfectives, which we know from the first part of the study, much weaker for perfective. Behavioral profiles, both complete and reduced, do equally well on both aspects, around 80%, which is much more than just pure guessing. Now you can zoom in into each of these linguistic types. Like this is just theoretic. Still, solid line is original one. Dashed line represent those empirical numbers turned into numbers. So Poisson and Gaussian. And you have those noisy ones, which are dotted lines. So here the situation is all 5 theoretical, original, empirical are doing roughly equally well. Poisson is doing slightly better than, but not significantly better than Gaussian. And interestingly enough, noisy ones are doing worse and worse if you allow more exemplars in your family, when you do comparison and assign new labels. So that's kind of interesting. So you see that they go down. Now about behavioral profiles. So again, dashed line represent those empirical embeddings, and dotted lines are random ones, noisy ones. So what you get here, they're weaker than theoretical. Original empirical are doing quite well, and there are not much difference. Again, Poisson is a bit better than Gaussian. And random ones are just quite worse, but they are not affected by neighborhood sizes. You can even say that maybe for perfective, they're doing a little bit better with larger neighborhoods. So you see that kind of upward line. You can imagine the one over there. But now the critical question, are LLM embeddings better? And I just asked Dagmar yesterday, am I the one guest psychologist who will tell linguists that they should retire? It's the end, it's doomsday. Well, really not. Black and, yeah, I think I will manage. Black is Herbert, so most often used. Gray is Roberta, most powerful. And if we just concentrate a little bit on this part of the graph, so the lower end, what we can conclude from this part is that they perform still above chance. But interestingly enough, they're very similar to noisy behavioral profiles. So when we only kept some information from original linguistic representations. I think it's just not by accident. There is a bit more, at least I'm reading more into this, maybe. I think that they're both LLMs or BERTs are bottom, and behavioral profiles are bottom up and data driven. You need data to annotate it. It kind of comes from usage. And they both only know if feature is the same or different, not much more. So LLM embeddings pick up random noise from usage in this particular task. So I don't want to claim this is in general. Many people who are actively developing large language models would say they're doing an awesome job on all kinds of cognitive tasks. They're super smart, better than us. But for assigning Polish aspect, which is basically a binary choice, and we know it's a difficult thing, not for us Slavs, but for many others. I think that that you can say that they pretty much are, I mean, I don't want to use rude word, but they're not great. But you can think, okay, is there a chance for linguists to engage? And what will happen if I now fuse linguistic information into LLMs? Will they perform better? So that's the final, like, okay, let's squeeze out everything that we can do. So now on this graph, you have only Herbert, because they did comparatively similar. Now dotted line is basically fusion between theoretic and LLM. And dotted blue is fusion between behavioral profiles and LLM. So what's the conclusion? Is if anything, they do slightly worse than originals. At best, their performance is like when you really translate all the possible information from original ones to numbers, to kind of Poisson or most probably Gaussian empirical embeddings. So linguists basically do not need LLM as much LLM might need linguists. My take-home message as cognitive psychologist, as guest here, I like to work with linguists more than with psychologists, and I'm very happy that our collaboration flourishes and we are going strong. I think we don't plan to end the collaboration yet. But my take-home message, I think there are a couple of interesting cognitive points. I think linguistic work is some sort of a sophisticated analysis of data and then synthesis into new knowledge which is meaningful or embedded in real world. And LLMs, we know that they're just very powerful pattern matchers or pattern recognizers. And currently with GPTs, they also are really powerful in predicting next most probable state. I just want to make a disclaimer. We used BERT rather than GPT because GPT is just better for production. This is basically a comprehension task. So there are no differences, and basically they're both transformers, so they do equally. There is no difference for this thing to bother with GPTs. But for me, cognitively, if I want to stay open-minded, it's really striking how far can you get with just stupid pattern matching? Store a lot of things and just find the best match and then do something with that. It tricked us. It passed during tests. So that's interesting more than what they actually can do. In summary, theoretical linguistic probably fails when neighborhoods are large and they are worse and perfective. Dagmar already said it's peculiar because we actually have more data. So somehow theoretical distributed representations are not combining well, mixed well with the data, with actual usage. While behavioral profiles, okay, first LLMs, they're weaker throughout. Again, if we really want to be fair, maybe that's partly due to the fact that we used the full bias spectrum of exemplars, because most of the time you really don't have a choice. Verb either prefers almost exclusively perfective or exclusively imperfective in most instances. Only in 11 to 12% of instances you have real ambiguity. So they will leverage that fact probabilistically and they will perform even better, just because in most instances you actually don't have a choice. It's just you sign, you know the pattern and you just say, yeah, it's imperfective because that word always uses imperfective, so there is no question here. But they don't have information. It seems that they don't have information to handle those ambiguous cases. BPs, they're not the best, but they're very stable across neighborhood sizes, so they're not affected by experience. They're also not, they perform equally well across possible outcomes, but they are not good if they're just random. If you just allow them to say it's the same, it's different. And we discovered something completely new, never heard in linguistics and psychology, that language use is contextual and meaningful. So yeah, it's a little bit anticlimactic, but that's where this gets us. The point here that I just want to reiterate what Dagmar already said is that we should really expand our tunnel vision into all instances, and if LLM uses full spectrum and then gets that awesome performances, linguists should stop focusing only on most peculiar cases. What I tease Dagmar is that linguists are like clinical psychologists, diagnosticians. They love specific instances of depression or eating disorder, something that is very unique. But you don't want, if you have a mind experiment and allow alien to learn about us, you don't want them to learn from one sentence about furious green ideas. You want some average sentence, that's a better sample for them to understand us. Also, an average person would serve better as a representative of human race than some specific instance or unique case. There are further studies that, if you're interested in what we presented here, on the left, we are done, so no worries, it's just like a final remark. On the left, you have a large-scale corpus-based study also using machine learning and computational modeling, published in Psychology, treating the same problem. And then on the right hand, it still is it online already? It's in a matter of days, it will come out. It's more applied. It considers the same problem of learning Polish aspect, but now in case of classroom interventions and different approaches to learning or mastering a spectral distinction. Thank you very much. Thank you.